go to the whiteboard and continue solving these problems. So you still have those values, the value of beta 0 and the value of beta 1. So we are going to continue from there. Then now we want a confidence interval. Now we want a confidence interval for the regression slope, which is given by beta 1 hat plus or minus the value from the table, which is the critical value, and the standard deviation of beta 1 hat. So this is called the standard deviation of beta 1 hat, or the standard error of beta 1 hat. And if you recall, the value here was 0.2625 plus or minus. So the value from the table is T alpha. Our alpha, because you still remember this, when you calculate the confidence interval, so our alpha is here. So our 95%, it tells us that it was 1 minus 0.5. So we have 0.95, and then you convert that to percentages, 95%. So our alpha is 5%. So we're going to have alpha of 5%, which is 0.05. And if you divide that by 2, we have 0.025. And our degrees of freedom, because our n is 10, so we'll have 10 minus 2, which is 8. So we are looking at T of 0.025 and 8%. So that's what we are looking at. And if you go to a student T distribution table, you go to a student T distribution table. So as you can see on the horizontal, we have those confidence levels. So we have 0.025 here and our 8 degrees of freedom here. You know how to find that value, so I'm not going to spend time there. So our value in this case is 2.306. So you know how to get that value. I'm not going to waste time. I just wanted to show you that our value is 2.306. And now, what is this? Because we need this value. What is this? This is the square root of s squared divided by SSXX. We calculated SSXX when we were estimating beta 1 hat. So what we are looking for now is s squared. So s squared is calculated by the formula SSYY minus beta 1 hat SSXY divided by n minus 2. And the value of SSYY we calculated earlier is 367452.4 minus beta 1 hat, which is 0.2625 multiplied by SSXY. And the value of SSXY was 1140. Okay, let me create a space so that I can write this. So I will substitute here. So the value here, I said it's 3667452.4 minus 0.2625 multiplied by 11846832.4 divided by 8. So this is divided by 10 minus 2. And the answer, what is the answer? What is the answer? It's 696911197. Are you all having that value? Are you all having that value? So that is our S squared. That is our S. I cannot hear you. Yes.
I'm giving a different value.
What are you having?
69707.
I understand. It's because of, remember what I said earlier? It's because of rounding. Remember, this value we have rounded. The value of beta 1 was not this, was 262511 something. So myself here, I did not use the 0.2625. I used the one that like the full value. So I did not round it. So if you replace this by the whole value of beta 1, you will get this.
Okay.
So because of space, I was not able to write that. That's why I'm using this one. But I said, you guys, when you press the calculator, you can always store the answer so that you can use it. It was for that reason. It was for that reason. So now we have our S, which is equal to this, or S squared. And our formula requires that S squared because we already have this one. Now this one we calculated earlier when we were estimating beta 1. So now we have calculated this. We can substitute there and get the confidence interval. So we can substitute them and get the confidence interval. So let's create a space so that we can have our confidence interval. So we are having 0.2625 plus or minus 2.306 into the square root of 69691.11917 divided by 45128.904.4. So this is what we're having. And if you press the calculator there, our interval is 0.17189. This is the lower limit, and the upper limit is, so that is our upper limit. And the interpretation is that we're 95% confident that the true regression slope it's covered in this interval. So it's between these two values. So the true regression slope is between this. Remember, this is an estimation. So this is a confidence or an interval estimation. So this tells us that at 95% level, the value of the true regression slope, the population value of the regression slope will be between these two values. Is it clear?
Yes, sir.
Thank you very much. So we can go to a 90% now, because this was a 95% confidence interval for the slope. So now we go to a 90% confidence interval for the model intercept. So now we are going for model intercept. Now the formula is beta 0 hat plus or minus T alpha over 2 n minus 2 S beta 0 hat, and S beta 0 hat, it's nothing but the square root of S squared into 1 over n plus x bar squared divided by SS xx. So this is what we're having. Remember the value of f of s, I mean, we already have. The value of SSXX we already have. X bar is simple because we have the summation of xi. So it's the summation of xi divided by 10 all squared. So that is x bar. And so what we need again is the value from the table, because it's not going to be the same. Here we're going to have our alpha, which is 10%, 10%, which is 0.1. So if you divide that by 2, we'll have 0.05, and the degrees of freedom is 8. And if you check from the tables are there even on internet, but also in the guide, I think the table is there. So this is 1.860. So this is the value from the table, is the critical value. And our beta 0 was 31. So if you are not following, please stop me so that I can try to explain. If you are not following, feel free to say no, you are not following, so that I can explain. So this is the critical value multiplied by the standard error or the standard deviation of the intercept, and we said is given by this. So our S was someone please press the calculator when I'm writing, because I did not calculate for this one. I don't have the calculations for this. So please, when I'm writing, write the, so it's 1 over n, our n is 10, plus our mean square. So our mean square, it's simple like this. It's going to be summation of xi, and the summation of xi is 42,074 divided by 10 all squared. I prefer doing it like this because I don't want to round the answers. So I calculate it straight from the calculator. I punch this as it is in the calculator so that I don't have a situation where I first calculate the mean and round it, because rounding the mean is going to influence the final result. So to avoid that, I calculate the mean like that in the calculator. So I just put it like that. When we say find the standard deviation of beta 0, we are not going to give you the mark for calculating the mean and stuff. No. So you can also do it like that, because there's no mark for getting this mean. And SSXX, it's 45, 1, 2, 8, 9, 0, 4.4. Raymond, you have the answers for these ones. Please provide us the answers. I cannot see what you are typing there, because I've projected the whiteboard. So please, if you have something to say, use the mic. Raymond, please help us with the answers here. What are the answers?
It's negative one,
Negative
negative
1,
312.596.
312 is 312
.596.
0.596. Then the other one,
376.4187.
376.4187.
4187.
Thank you. So this is a confidence interval, or a 90% confidence interval for the true regression intercept. So this tells us that our regression intercept will be between these values. And something it's not right here, because if you look at this estimate, it's not included or covered in the interval. So if you look at the estimate, it's not covered in the in the interval. So we'll see as we proceed. Are you all having that value? Or are you all having these limits?
Yeah.
The upper and the lower?
Yes. Yes, sir.
Yeah.
Okay. Okay, thank you. So now the next question is the confidence interval for the individual value of X, or the individual value of Y, which is the revenue for bands. So what we need now is to go and check. Now let me project this. What we need is the value of X for bands. So the value of X for bands was 2278. The value of X for bands was 2278. So we're going to use that value here. We're going to use that value because the formula is like this. The formula is like this. So we're going to get Y hat for bands plus or minus T alpha over 2 n minus 2, then the standard deviation. And the standard deviation is given by the square root of S squared into 1 over n plus X for bands minus the mean, which is X bar, all squared. They are divided by SS XX. So the formulas are there in the guide. So this is what we are going to get. So what we need now is YI hat for bands. So we're going to calculate YI hat for bands, and that will be given by this, which is 81.9114 plus 0.2625, and we substitute that value for bands, which was 2287, and we get the value here. And what is the value? If you press your calculator, what do we get there? What do we get there?
Sir,
Yes.
are we calculating for the individual or for the mean?
For the individual, we're estimating for the individual. The first one we're estimating for the individual, then the second one we're estimating for the mean. And remember, the confidence interval for the individual and the mean, this value is the same. The difference is on the standard deviation. We explained that, we discussed that. So for the individual and for the mean, the difference is only on the standard deviation, but the point estimate is the same.
So, sir, isn't it that the standard deviation for the individual, the square root inside, isn't it
Sorry.
1 plus?
Thank you. 1 plus.
Yes.
Thank you for that. Thank you. So what is the value here?
632.
Guys, you must have calculators and press these things, and also check here if we are doing the right things. So you must also check if we are doing the right things. So the point estimate is this one. So we can substitute here by the point estimate. Then the value here, it's 95%.
Sir,
Yes.
the value of X is 2278, not 2287.
Thank you. So it's 2278. And then if that is the case, then our value is going to be 629.
629.
So it's going to be 629. So it's going to be
0.88.
629.8864.
64.
So now we take this value and substitute it there, which is 629.8864 plus or minus 2.306. Now we're going to have here the s squared, and the value of s squared we said is 691.11917 into 1 plus 1 over 10 plus, now we have the value here, you said it's 2278 minus the mean squared. So the mean squared is going to be 42. No, the mean is not squared in this case. Sorry about that. It's just the mean, and then we square everything. We square this. So it's going to be this minus the mean, and our mean is going to be 4240. Okay, let me create a space. I will write it here so that everyone can see. I'll write it here so that everyone can see. So let me do it like this. Create a space. So I'm going to write that part inside the square root here. The last part, which is 2278 minus the mean, which is 42074 divided by 10. So all this all squared, and then we divide this part again by SSXX, and that value is 45128904.4. So you punch the calculator. So this part must be here. So please put that one there and punch the calculator and give us the confidence limit. What is the confidence limit? Raymond, assist us. Raymond, assist us. Guys,
I'm still calculating.
I know that we have calculators. You just press the calculator and give me the values. So you guys don't know how to press the calculator?
Sir,
Yes.
I got 1291.
No, let's
Comma.
start. It's 1 2. It's 1 2
9 1
9 1 comma
8936.
8936. Then the other one,
Yeah, as for the other one.
you just replace minus by plus there. You don't recapture everything. You just go and delete minus here and put plus. Then you get the answer.
Yes. It's negative 32.
Something is not right again. You cannot have the upper limit as a positive, then the other one as a negative. Something is not right there. Check your calculations.
Yeah.
So it's fine. It's fine. You will go and press the calculator because you don't want to talk and you have this.
I got
it's a matter of pressing the calculator. So you will go and press the calculator. The procedure is there. The values are there. What is left is for you to press the calculator and record the answer. So you will go and do that one because you don't want to talk. You don't want to share the values. So the next one is a 95% confidence interval for the mean. And the difference between the individual and the mean is on the standard deviation. So the standard deviation for the individual, it's S into 1, I mean for the mean over N plus XP minus X bar squared divided by SS XX. And that difference is here. This one for the individual, there's 1. And this one, there's no 1. So what you are going to do is to remove 1, then leave everything as it is, then you get the interval. So that is the difference. You are going to remove 1 from inside the square root from the standard deviation, and then you press the calculator, you get the answer. Yes, Malek, you are recognized.
Hello.
Yes.
Can you please go back to the questions for like 2 seconds?
Here are the questions. And
Okay, it's fine. I got it.
yes, and again, the value there, remember, this was for bands. So the procedure is the same. Here you are going for Honda, which means the value of X is going to be 2535. So it's no longer going to be 2278. So now we are going for bands. I mean for Honda, not bands. So that's another thing that you should pay attention to. So that is how to get those confidence intervals, and you know that the how to interpret the confidence interval. And you can also test specifically or especially the first two. You can test whether I mean the first one, which is number B, the one for the slope. So you can test if there's a relationship using that confidence interval. So you can test for the relationship. If 0 is included in the interval, it means there's no relationship. Because if 0 is included, it means there's a possibility that beta 1 can be 0. And if beta 1 is 0, it means there's no relationship between x and y. So now we're going to F, which is about ANOVA table. So we're going to test using ANOVA table. And what we need from the ANOVA table is or let me have the skeleton of the ANOVA table so that you can see what I'm talking about. So in the ANOVA table, the first column is the source of variation. So we're going to have the source of variation. Then we have the degrees of freedom. We have the sum of squares. We have the mean square. And we have the F ratio. And the first one is regression. It's regression, followed by the error, followed by the total. And we said the degrees of freedom for the regression is always, for simple linear regression, by the way, for simple linear regression, it's always 1, because it's p minus 1. P is the number of parameters. So we have 2 parameters. So it's 2 minus 1, which is 1. And this one is n minus 2. Our n is 8, is 10. And then 10 minus 2 is going to be 8. And this one we said is the sum of this. Remember, to get this, we partitioned the total variation. So when we add these two, we're going to get 9, which is n minus 1, by the way. And here we want to find the value of SS reg. Here we find the value of SSE. The value of SSE we already have. Remember, we estimated S squared. So S squared is SSE divided by these degrees of freedom. And that value here, we obtained it to be 69691.11917. So we have the MSE because MSE is equal to S squared. So to get this, because to get this, we divided this by 8. So to get this one, we can multiply this by 8. So if we multiply this by 8, we're going to get the value there. And if we do that, which is 69691.11917 multiplied by 8, and we get, of course, there's the formula. This is not the only way of doing this. So you can also plug in these values in the formula and you get the value. You get this value, 95. So that's how to get that value. And we know that the value of SS reg is the same as the MS reg. So that value is the same. So we're going to calculate SS reg. And SS reg, we're going to get it from the formula, which is beta 1 hat SS XY. And beta 1 we said is 0.2625. And SS XY we calculated, we said it's 118,468,32.4. So this is what we're having. So if we punch the calculator there, we're going to get 505. So this value is for these two cycles because those two are sharing the value. The SS reg is same as MS reg. So we're going to have that value here. I will just write it inside this rectangle to show that is the value for the two columns. Is the value for the two columns. Because of space, I will write it like this. And when we add these two, we must get the total. Remember, the total is the sum of the two. So we partitioned those two values to get we partition the total into two to get those two values. So we can add the two values and get the total. And when you do that, the total is going to be 86,09072.455. So this is the SS total. Then you have the MSE and the MSR. When you divide MSR by F, MSR by MSE, we get F. And what is our F value? You are recognized.
Sir,
Yes.
are you sure you did not make a mistake on the SSR and MS?
No, the possibility is there because remember I'm saying give me the values. You don't want to talk. So now I'm showing you the procedure how to get these values. So you can press your calculator. Then if there is a mistake on my values, then we'll take it from there. Because the thing is, I'm saying give me the values and you don't want to talk. So I cannot tell whether I made the mistake while punching the calculator or not.
The correct one, sir, is 31.
31.
099.
You're saying is 099.
23.447.
0.447. It's fine. I suspect again is the matter of rounding these values. So if that value is correct, then it's fine. You can use that one. It's the matter of rounding because when I say what is the value here, this is the steps. Punch the calculator and give me the answer. You don't talk. So and because We have to do these things. We cannot just keep quiet because you guys don't want to talk. So I just press my calculator and get this. And because I'm pressing and writing, obviously I have to round these values. But that is the way of doing it. Thank you very much for that. Thank you very much for that. So when you do that, when you take the ratio there, you will find the value of f. When you take the ratio there, you will find the value of f, and the value of f is nothing but 4.47. So the value of f here is 4.47. So this is our ANOVA table, and this is our f ratio, or the value of f. And remember, we want to test a hypothesis here. We want to test a hypothesis here. So we have to move to find the f tabulated so that we can compare with this value. We are going to need the f tabulated so that we can compare with this value. Yes.
On the f calculated, can you use the correct one?
What is the correct one?
Which is 44.62.
44?
Yes, 44.62. Yes.
Are you all having 44? Are you all having 44? You are saying it's 44 point?
It's 44.62.
44.62. Thank you. So that is the answer. And you can see that this value is very far from 1. Remember what we discussed earlier, that if beta 1 is equal to 0, this value shouldn't be far from 1. So if the answer is 44.6, you can see that it's far from 1. And that tells us that beta 1 is not equal to 0. So you can reach that conclusion that beta 1 is not equal to 0. And even the confidence interval, because if you recall that confidence interval, we were having something like 0.17189. So 0 was not included in this interval. And this tells us that there's no way that beta 1 can be 0. So the conclusion that we are reaching using the f value and also using the confidence interval is the same. So these two procedures are taking us to the same conclusion. But you can also compare this with the f calculated. You can go to the table. You can go to the table and check. Yes, I'm listening.
44.62 is it the value of f?
That's what he said.
No,
so you can go to f. Yes, that's why I was asking if you guys are having the same answer. But what matters is the procedure here. If you understand what we are doing, because when I say punch in the calculator and give me the value, you keep quiet. So now the value, whether it's 2 or 3, it does not matter. What matters is, can you conclude? But in the test, obviously, you will have to provide the correct values, because there you are forced to punch in the calculator, because here you don't want to use your calculators. So in the test, you are going to use your calculators. So you can compare that value, whether it's the 4.4 or the 44.6, you can also compare it with the value from the F table. You can also get it from the F table. And that value is, can someone please help us with the value from the F table? If you have the F table, what is the value for 5%? Don't divide alpha by 2. For F, we don't divide alpha by 2. For F, we don't divide alpha by 2. So can someone please help us with that value there?
You are still calculating, sir.
No, you don't calculate this value, you take it from the table. You don't calculate. That one is not true that you are calculating. We don't calculate for F. You go to the table and take the value there. Let me just check my statistical tables. So here there's no F. I can go to internet, it's fine. Now I can go to internet and find that one. F distribution table. F distribution table. 5%. So let me check what am I having here. So no. I don't want this. I don't want the video. What are you guys having from the F table? Okay, it is. So our degrees of freedom, it's our degrees of freedom, it's 1 and 8. What are you having? Myself, I'm having 3.46. 3.46. Are you having that? 3.46. I'm having 3.46. Are you having 3.46? So the value that I'm getting from the table is 3.46. And if you compare, the calculated is greater than the tabulated, which means the calculated is inside the rejection region. So we're going to reject the claim that beta 1 is equal to 0. We're going to claim that we're going to reject the claim that beta 1 is equal to 0. So whether you have compared you have concluded using comparing the two values, the expected value of the MSE and the expected value of the MSR, or you concluded using the confidence interval, or you checked whether the calculated is inside the rejection region, they take you to the same conclusion. Is it clear?
Sir,
Is that one clear? Yes.
how did you say we conclude the first time?
No, the conclusion is the same as the one that I just gave now. You are rejecting the claim that beta 1 is equal to 0. The interval tells you that beta 1 is not equal to 0. The value there is not close to 1. The F ratio is not close to 1, which tells you that beta 1 is not equal to 0. Remember earlier, or in the first class or in the morning, we discussed that if beta 1 is equal to 0, the expected value of MSR will be equal to the expected value of MSE. And if those two expected values are not equal, yes.
I was saying about the MSE and the SST. You said something about.
That's what I'm explaining now. That's what I'm explaining. That we discussed earlier that if beta 1 is equal to 0, then the expected value of MSR will be equal to the expected value of MSE, and which will be sigma. And if that is the case, when you divide the two, the ratio should be 1 or close to 1, because the values might be not necessarily equal, but very close to each other. So that one will tell us that there's a possibility that beta 1 can be 0, like it's very close to 0. So in this case, you can tell that from the answer that we obtained, it's not the case. And I said you can also confirm your conclusion by using or by comparing the calculated and the tabulated. And I did that as well. And we obtained that the calculated, either you take 4.4 or you take 44.6 as compared to 3.6. Those ones are greater than 3.6. So they are inside the rejection region. Then you can reject the claim that beta 1 is equal to it's equal to 0. It's time for break. Let's take a 10 minutes break. We'll resume at 5 minutes to 2.
So if the value falls below the calculated one, we accept.
We fail to reject, yes. If the
Oh,
calculated is less than the tabulated, we fail to reject the claim.
all right.
Yes. Welcome back. I want to believe that you can hear me. So this is the summary output. So the correct value was 44.62. So whoever gave us that value, thank you very much for that. So that was the correct value. It's 44.62. So you will go and press the calculator. Remember, I asked you to press the calculator and give me the answer, and you did not want to share your values with us. So the person who gave us that value, it was correct, the one of 44.62. So thank you very much for that. So you can see here, even our p-value is very small. If you recall, we always say that if the p-value is less than alpha, you reject the null hypothesis. And in our case, our alpha was 0.05. So because alpha was 0.05 and the p-value, as you can see, is small, then we reject. You reject if the p-value is less than alpha. 0.0001 is less than 0.05. So we reject the null hypothesis. So you can use the p-value. You can use the f. By looking at f, it's not close to 1. So it tells you that MSR is not the same, or the expected value of MSR is not the same as the expected value of MSE. And that tells you that beta 1 is not equal to 0. So you can also go to the conclusion using that approach. You can also use the confidence interval, as you can see here, where the confidence limits. So you can also say that the 0 is not contained in the interval, which means there's no possibility of beta 1 being 0. So that tells us that the test H0 must be rejected. So you reject H0 like that. You can also use the t-test. Here's the t-test. Remember the t-tabulated was 2.306. So as you can see, the t calculated is greater than the t tabulated. 6.68 is greater than 2.306. So even this one tells us that we must reject the null hypothesis. We must reject H0. Even the p-value, for t, it's less than alpha. And this one suggests as well that the null hypothesis must be rejected. Is it clear? Is it clear? So let's proceed and look at the last section of this chapter. And look at the last section of this chapter, which is correlation analysis. So we have been discussing regression analysis. We've been discussing regression analysis where we're examining the relationship between X and Y. So we can continue to check whether the relationship exists between the response variable and the predictor variable, which is X and Y, using the correlation analysis. And as you can see there, you can do this by the use of a scatter diagram. You can also achieve that by using the correlation coefficient and also hypothesis testing. Someone asked earlier if we are going to look at hypothesis testing for correlation. So this is the way of testing the relationship or checking the relationship using the correlation analysis. So the scatter diagram is the same as the scatter diagram that we use to examine the relationship under regression analysis. So you plot the values of x or the values of y with the corresponding values of x. So you plot the values of the response variable with the corresponding value of x. So the values of y with the values of x, as you can see on the pictures there. So the first one tells us that there is a positive correlation between x and y. You can see from the picture or from the scatter plot that there is a positive correlation. And then the second one, you can see that as the values of x or as the values of x increases, the values of y decreases. So there is a negative correlation there between x and y. And if you look at number 4, this tells us that there is a perfect positive correlation. As you can see, those dots there are on the line. So there is a perfect positive correlation. And the fourth one, there's a perfect negative correlation between x and y. And if you look at this one, number 5 there, tells us that there's no correlation at all because we cannot tell what is happening. There's no picture of what is happening here. There's no picture of what is happening here. So there's no correlation. There's no association between x and y. So you cannot tell whether the value of x or the values of y increases or decreases as the value of x increases or decreases. So you cannot tell that. And then the last one, you can see that at some point the values of x were the values of y were decreasing and the values of x were increasing. Then there was a turning point there. The values of y started increasing at some point as the values of x were increasing as well. So you can see that there is some sort of association, but it's not linear. So that's another thing that we can get from, or that's the thing that we can get from the last picture there. So you see that the values of x were or the values of y were decreasing as the predictor values were, or the values of the predictor variables were increasing. Then we had a turning point there where the values of y started increasing as the values of x was or were decreasing. So that's what we are getting there. So that's how to use the scatter plot to check the correlation. So the only thing that we can tell using the scatter plot is that there is a positive correlation, there is a negative correlation, there's a perfect correlation, or there's no correlation, or there's no linear correlation. That's what you can get from the scatter plot. Yes, the Matato.
So I had a network problem, Yana, so I didn't hear you on the first 2 scatter plots. Can you please?
Okay. So on the first 2, if you look at the first 2, they are not the same as this one, even though the direction is the same. So if you look at the first 2, they're same as the third and the fourth, but the direction, the direction is the same, but the dots there are not the same. So number 3, you can see that these dots are perfect, are on the line, but these ones are not perfect, because if you were to draw a line here, you will see that some of the dots will not be on the line. So the first one only tells us that there is a positive correlation between x and y. We can see that the values of y increases as the values of x increases. So the second one tells us that the values of y decreases as the values of x increases. So there is a negative correlation. That's what we get. But 3 and 4 tells us that this correlation is perfect. It's positive and perfect. It's negative and perfect. And number 5, there's nothing at all. And number 6, there is an association, but it's not linear. That's what we get from the scatter plot. But the correlation coefficient measures this relationship. We can say that it's positive, but we don't know how strong is this correlation or this association. So the correlation coefficient measures the strength of the relationship, tells us how weak is this relationship. So the correlation coefficient helps us with that, telling us how weak is this relationship. Because with the correlation coefficient, I can tell that the correlation coefficient for the third picture, for example, the value is 1 there. It's perfect. So the correlation coefficient is going to be 1. But for the first one, I cannot tell. I can just tell you that it might be between this and this, because I can see that it's positive, but I don't know how strong it is. So when you calculate the correlation coefficient or the value, it tells you how strong is this relationship. So, and these are the ways of how one can interpret the value. So the correlation coefficient is a number between -1 and 1. So if you get the correlation coefficient which is greater than 1 or less than -1, then something is not right. So the correlation coefficient is between the two values. So if the value is close to 1 or it's 1, it tells us that there is a perfect correlation. Or if the value is close to -1, it tells us that there is a perfect negative relationship. So there's a perfect negative. And well, the correlation coefficient is 0. That tells us that there's no association between, or there's no linear association between the two variables. And then I will share with you how to interpret the in-betweens. When when R is equal to 5 or 0.5, which is 50%, it tells us that there is a moderate correlation. So I will share the other interpretations of the correlation coefficient. Now, we have the formula of calculating, because we are saying the correlation coefficient is the value between -1 and 1. So we have to calculate this value. And here's the formula of calculating the correlation coefficient, or the value of the correlation coefficient is given by SSXY divided by the square root of SSXX multiplied by SSXY. YY, sorry. So it's SSXY divided by the square root of SSXX multiplied by SSYY. So that is the formula. And if you look at this, we know from section 3, which is the regression analysis, that SSXY, it's nothing but beta 1 multiplied by SSXX. And if we replace this part in the numerator by beta 1 SSXX, then we are going to obtain this. So I will do that on the whiteboard so that you can understand. So I will project the whiteboard and cover that part so that you can understand. And then from there we look at the example. Or before example, we look at the coefficient of determination. So what we're getting from there is that R, which is the correlation coefficient, it's equal to this divided by the square root of SSXX, XX, YY. And we know that beta 1 hat, it's SSXY divided by SSXX. So if we make this subject of the formula, we are going to have to replace this by beta 1 hat SSXX divided by, this one can be written as this. The square root of AB is the same as the square root of A multiplied by the square root of B. So now this is to the power plus 1, this is to the power negative 1. When the base are the same, we add the exponents. So if we do that, this is going to be plus 1 over 2, because we are having SSXX multiplied by SSXX to the power negative. So when the base are the same, we add the exponents. So 1 plus negative 1 over 2 will give us 1 over 2. And that will give us beta 1 hat. This part now will be having the square root because of that 1 over 2. SSXX all divided by the root of SSYY. Is it clear? Is it clear?
Yeah,
So
it's clear.
that's how to get the correlation coefficient. And because this can be negative, so if our R is negative, it means our beta 1 is negative. It means our SSXY is negative, because this can not be negative. So for beta 1 to be negative, it means SSXY must be negative. And because the R as well also depend on this. So if beta 1 is negative, it means your R must also be negative. So that is the relationship that you must know. You must pay attention to that. So if you are given beta 1 and you are asked to find R, so you must be able to know that the sign of beta is guiding you in terms of what will be the sign of R. And the scatter plot as well is if there's a negative correlation using the scatter plot. If there's a negative correlation using the scatter plot, it means the beta is negative. Beta 1 is negative. It means obviously R is also negative. So you must pay attention to those kind of things. Don't rush when you are given question and assume that no, this is simple and you do it like that. These small details are very important when you are answering questions. These small details that I'm giving you, you will need these details. So please pay attention to those kind of things when you are solving questions. Let's proceed. So that was about R squared. I mean R, which is the correlation coefficient. And now we're going to R squared. We're not going to test the correlation coefficient, but I've provided the notes there for those who are interested. We can also test for linear relationship using the correlation coefficient. So this is the formula for the test statistic. So we can also test if we want to do that. And the tabulated value will be the same as the one we have been using. So if you want to test, but we're not going to test, so let me not waste time on that one. And then the last part is the correlation coefficient of determination, which is R squared. So we can just square the correlation coefficient to get the coefficient of determination. It's simple like that. So R squared, or coefficient of determination, is nothing but the correlation coefficient squared. And what does this do? Remember, we said the correlation coefficient measures the strength of the relationship. So what does this do? The coefficient of determination. Mperon, you are recognized.
So the notes which you're going through, like they're not in my guide. I'm not understanding. Not all of them are in my guide. So.
Yes, like I said in the morning, I said what you need is in the guide. The part that is not in your guide are the things that I'm saying. So because I don't want to forget them, I write them down. But these are taken from the guide. If you go to your guide before inference of the regression slope or regression coefficient or regression parameters, you will find these notes about the coefficient of determination and the R. So these notes are there.
Okay, so would it be possible for you to like to post the exact
No,
slide?
it's not going to be possible. These notes are taken from the study guide. So I just go and put right statements that I will need when I'm explaining to you. And that's what I'm doing here. So otherwise I would have just uploaded this and not come here. So the reason I'm not sharing this is because I'm taking these things from the guide. I just find a better way of explaining them. Then I add those words in the notes so that when I project them, I remember that, oh, I have to also tell you about that. I also have to tell you about that. So these are here to remind me, but the things that you need are there on the guide.
Okay, so, yeah, because I've got fears that I might be confident in what I've studied, finding out that I've left some other stuff out. So just want to
No,
make sure
you
that
can.
I've got the.
No, the things that are in the guide covers everything.
Okay, sir.
Thank you very much. So we have the coefficient of determination. And as I was saying that the correlation coefficient measures the strength of the relationship between X and Y. And this correlation coefficient, we are told that is a descriptive measure that is commonly used to describe the degree of linear association. So this tells us in terms of percentage, how many percent of the variation. Remember what we were dealing with before ANOVA. We're explaining that this measures the total variation, this measures what. So R squared tells us how many percentage of the, or in terms of the variation is explained by our model. We calculated the figure there, the total variation explained by the model. We calculated in ANOVA, and we said that is SSR. But if you divide SSR, which is the variation explained by the model, by the total, you get the percentage, and that will give us the total percentage of the variation that is explained by the model. Now, it's more like calculating the probability, because if A is the event of the total variation, and you divide the number of elements in A by the total of elements in the sample space, you get the probability. So that's what we are doing here. We want to know the percentage of the variation that is explained by our model. And we get that by dividing the number or the total variation explained by the model by the total variation, which is going to be the variation explained by the model and the variation that is not explained by the model. And that will give us R squared. So now we know in terms of percentage, how many percentages are of the total variation is explained by the model. Is it clear what R does, or R squared? Because R measures the strength of relationship, only tells us how weak is the relationship or how strong is the relationship. But R squared tells us in terms of percentage, how much of the total variation it's accounted for by our model. And the r squared, the value of r squared is between 0 and 1. So it's more like of a probability, as I've said, that it gives us the probability of the event of the variation explained by the model. That's what we are getting there. And another thing is that if r squared is equal to 1, if r squared is equal to 1, it means what? There's no error. If r squared is equal to 1, as you can see here, if r squared is equal to 1, it means this error term, or the error sum of squares, is equal to 0. So this part is going to disappear and our r is going to be 1. And this will tell us that we have a scatter plot like this. We have a perfect relationship. We have a perfect relationship. So if our r squared is equal to 1, we know that there is a perfect relationship. But if our r squared is equal to 0, if our r squared is equal to 0, then this tells us that none of the total variation is explained by the model. So our model is, I don't want to say it's useless, but I will say that with a caution that it cannot be trusted, because 0 of the total variation is explained by the model, which means the error there is too much. Our error is equal to the total variation. I'm not sure if that makes sense. So if our r squared is equal to 1, it means there's no error. There's a perfect association between x and y. And this is the formula for calculating r squared. Here we said you can use SSR divided by SST. And you can also, because it's squaring R, the correlation coefficient. So we know that the correlation coefficient is SSXY divided by the square root of SSYY and SSXX. Then when you square that, you are going to get R squared. And R squared tells us in terms of percentage, the sample variation in the variable Y, which is the total variation, because the variation in the response variable is the total variation. So this tells us in terms of percentage the total variation that is explained by the model. So that tells us the total variation that is explained by the model. So now you know the difference between R and R squared. R squared measures the strength of the relationship, and R measures the strength of the relationship, tells us how strong is the relationship, how weak is the relationship, and R squared tells us how many percentage of the total variation. Remember, we partitioned the total variation SST into 2, which is the variation explained by the model and the variation that is not explained by the model. So R squared tells us in terms of percentages how much of the total variation is explained by the model. That's what we are getting from these two. So you must know the difference. You must know the difference of the two. So let's go back to that question of ANOVA. Then we look at the value of R, because it's provided there. When we run the results, we get the value of R. So we can interpret R from there. We can interpret R from there. Malek, you are recognized.
Yes, sir. Can you please just repeat the interpretation just one more time?
No, I'm saying R, which is the correlation coefficient, tells us the strength of the relationship. How weak is this relationship? How strong is this relationship? That's what we are getting from the correlation coefficient. But R squared, which is the coefficient of determination, tells us how many percentages of the total variation is explained by our model, or it's accounted for by our model.
Oh, okay,
Remember,
okay.
when we're dealing with ANOVA table, we said we are going to partition the total variation SST into two parts, and those two parts were SSR, which is the variation explained by the model, and SSE, which is the variation unexplained for by the model. So we have those two parts. Now we are interested in knowing now in terms of percentage, because the figure we can get from the ANOVA, but in terms of percentage, how do we get that? Then we bring in R. So R answers that question to see. No, in terms of percentages, this is the percentage. So you are going to divide SSR by SST. You get that percentage. So that's what we get from the R squared. So if you look at this output, now you have these values, by the way. You have the SSXY, SSXX, and so you can substitute from the formula and check if they are giving you this value that we are having. So you can do that. You can do that. So I'm not writing that one down, because you don't, when I ask you what is the value when you punch the calculator, you don't give me the answer. So I calculate using Excel, because with Excel it's fast like that. But you are going to substitute those values I gave you in the equation, and you check if they are giving you this answer. So our R
Sorry.
squared, and again, you must not be confused. We have multiple R, we have R squared, we have adjusted R, and so forth. As we are interested in R squared, and if we round this, is going to give us about 85%. And this tells us that 85% of the total variation is explained by our model. So when we divide the total variation into two parts, 85% of that total variation went to SSR. It's explained by the model. And 15% it's explained by the error. And one would say, this is not bad. We can trust our model, because the error it's slim, 15% as compared to 85%, something like that. But what is our value of R? Because this is R squared. We also want to know the value of R. The value of R is the square root of this. But taking the square root alone, it's not enough, because if you take a square root, it's plus or minus. So you have to decide on the sign. As I've indicated, that beta 1 will guide us in terms of the sign. So you check beta 1. Because our beta 1 is positive, it means our R must be positive as well. So you are going to check here that value. So I'm going to calculate R for this one, which is going to be the square root of that. And our R, it's 92, is 0.92. That is our value of R, it's 0.92. It's almost the same as this one. So this tells us that is the same, is the method of rounding. If I open this, you will see. So our R is here, which is the square root of this. So this tells us that there is some sort of a perfect positive relationship, or a strong positive linear correlation between X and Y. So you can get that from the R there. Another thing, R squared, if this column or this output was not given, we said you can also get R by dividing SS reg by, you divide this by, the SS total, and that was going to give us this answer. So as you can see, this answer is the same as this one. So you must know that even if you are not given this, you can get R squared from the ANOVA table. You take the variation explained by the model by the total variation, and that will give you the variation in terms of percentage that is accounted for by the model. Is it clear? Is it clear?
Yes.
Thank you very much. It's now 2:30, so we are done for today. I'm going to stop here, and this concludes, or yes, concludes the I'm not going to come back to this. Concludes the first chapter. So we are done with chapter 1. When we meet next week, we are going to look at chapter 2. You are reminded again. You are writing your first quiz next week, Friday. We'll discuss the time next week, Thursday. And you are writing test 1 on the 11th of March. Class reps, remind those who are not with us that they are writing their first quiz next week, Friday, and test 1 on the 11th. So please make share that message with them. Go and prepare. The scope of the quiz is chapter 1. So it's everything that we have covered until today. And as I've indicated that